Hey everyone, today we're going to take a look in statistics at section 6.1 let's just go right to it. So we've got this count up the number of children in your family including yourself. Be sure to include all your stepsisters, stepbrothers, half-brothers, half-sisters. So let X be the number of children and suppose that we choose someone from the class randomly. So what's missing here is we've gone ahead and we've counted everybody in class. This is class last year. We had 30 students in stats, and we had 6 of them had 6 out of the 30 had one sibling, 12 out of the 30 had 2 siblings, etc., down the line. So is this a valid probability model? Okay, all the probabilities add up to 1, and all the probabilities are between 0 and 1. So yes, this is a valid probability model. Is 5.7167 a possible value for X, and explain? I think that answer is no. The number of children in a family has to be a whole number. And what this brings up the idea of a discrete probability model. And in a discrete probability model, only a few outcomes are valid. So in this case, only outcomes that are integer values are valid in the probability model. That kind of contrasts with what we would call a continuous probability model, where any value would be admissible as an outcome. But we'll get to the continuous probability model later. Right now we're concentrating on this discrete probability model. So the next thing here is to make a histogram to display the information in X on a horizontal axis, and then we're going to describe that shape. Popping that information over into Statlet, we can create a histogram really quick. One thing I want you to notice with this is that all of these bars are centered on the integer values of the number of children, not centered at, well, not starting from 0 and going to 1, or going from 1 and then going to 0, but it being centered at 1. And that's the correct way for us to deal with integer values here for a discrete probability distribution. So then we're supposed to describe the shape, and this is a bit of a throwback question, but the number of siblings is a right skew single peak distribution with a median of 2 siblings and an IQR of 1 sibling. All right, so remember that is center, shape, variability, and unusual features. There are no outliers in this distribution, so it might be a good idea to mention that. Number 4, describe in words what p x greater than equal to 3, what is that? And then find that. Well, if x is the number of children, then we're saying what's the probability that a randomly selected child has 3 or more siblings. More eloquently, px greater than equal to 3 is the probability that a randomly selected student comes from a family of 3 or more children. And the probability that x is greater than equal to 3, that's just 8 over 30 plus 3 over 30 plus 1 over 30, which ultimately equals 0.4. And where do those numbers come from? Okay, 8 over 30 for 3, 4 over 30 for, or 3 over 30 for 4, 5 is 1 over 30, and 6 is 0 over 30. So we're just adding all of the columns that are 3 or greater. What about describe in words that probability x is greater than 3, and then find that? Okay, well, the probability that x is greater than 3 strictly is the probability that a randomly selected student comes from a family of strictly more than 3 children. So now we're not going to include 3. So the probability that x is strictly greater than 3 is 3 out of 30, 1 out of 30, which is 4 out of 30, or ultimately 0.1333. Remember, for probability that x is greater than or equal to 3, that's a probability of 4 plus the probability of 5. Okay, now we're going to find the average of the x values. Okay, all the x values that were valid here were 1, 2, 3, 4, and 5. And so when we add those and divide by 5, we get 3. So does that number tell us the average number of students, or the number of children in the families of students in this class? I don't know. Let's look at our histogram, and where is 3? Let's zoom in here. 3 is right here. Does that look like the average? No, it looks like the middle of the data, but it doesn't look like the average. So the average should probably be somewhere close to the left of 3, maybe around 2.5. So 3 looks like it's too far up to the right of the data to be the average number of children in families. So we can't just add up all of the x values and divide by 5. Now that is a classic mistake to finding averages. What we need to do is to find what's called a weighted average, since some values are more weighted than the others. In other words, the influence of having 2 children should be greater than the influence of having 5 children, since just looking at the histogram, there are more families with 2 children than there are with just 1 children. So the way to do that with the weighted average is you're going to add up all of the x values multiplied by their corresponding probabilities. So we can see the average is going to be 1 multiplied by 6 out of 30, plus 2 multiplied by 12 out of 30, plus 3 multiplied by its probability, which was 8 out of 30, 4 multiplied by the probability of a 4, which is 3 out of 30, plus 5 multiplied by the probability of a 5, which is 1 out of 30. That's equal to 2.367, which, as predicted, is a bit to the left of 3. So this is where we go with this. We have discrete random variables. Remember, we talked about these were discrete values because there were only a certain number of values that were admissible. Usually we're talking about integers. And these are random variables because it is a probability distribution for discrete quantitative values. We have learning target 1 is this idea of discrete random variables versus continuous random variables. A discrete random variable can take on a fixed set of possible values with gaps in between the values. Now the gaps in between the values, that's just something that's kind of added in there to make you more aware of what a discrete random variable is. So if you see, a random variable can be 1, and then it can be 2, but it can't be a number between 1 and 2, then you're looking at a discrete random variable. Continuous random variables can take on any value in an interval. So if my interval is from 1 to 4, then my continuous random variable could be 2.3 or maybe 3.111. Those all have a possibility of outcome, of being an outcome. We did a lot of histograms before. The only difference here with the histogram on a discrete random variable is that your value should be centered on the histogram bar. We also had experience just now with finding the mean of a discrete random variable, and that's just adding up the outcome multiplied by the probability of that outcome. Add them all together. Don't let that formula scare you into thinking that it's more than it is. It's not really very much. So let's check our understanding. Indiana University Bloomington boasts a grade distribution posts, why did I say boast? Posts the grade distribution for its courses online. Suppose we choose a student at random from a recent semester of the university's business statistics course. The student's grade on a 4-point scale with an A equals 4 is a random variable x with the following probability distribution. Write the event the student got a C using this probability notation. Okay, well, what is a C? Well, if an A is a 4, then a B must be a 3, then a C has to be a 2. So the probability that x equals 2, well, we have a bunch of question marks. I'm pretty sure that's not the correct answer here. So to figure this out, you're going to use a property that all of these probabilities have to add up to 1. So we're going to take 1 and subtract from it 0.11 plus 0.032 plus 0.362 plus 0.5457. That gives us 0.138. Okay, explain in words what x equals greater than equal to 3 means and find that probability. First thing is, what is x? Okay, so a student's grade in business statistics. Probability that x is greater than equal to 3 is the probability that a randomly selected business statistics student has a grade of a 3 or higher. Okay, which outcomes are greater than equal to 3? That is, 3 is greater than equal to 3 and 4 is greater than equal to 3. So the probability that x is greater than equal to 3 is equal to the probability that x equals 3 plus the probability that x equals 4, which is ultimately 0.819. 3. Make a histogram of the probability distribution and describe its shape. Okay, just very simply, we've got that the histogram here looks like a left-skewed distribution. And lastly, calculate and interpret the expected value of x. Expected value of x is the same thing as the mean. So this question is, calculate the mean. Okay, so we've got 0 multiplied by the probability of 0, 1 times probability that the GPA is a 1, 2 multiplied by the probability that a GPA is a 2, 3 multiplied by the probability that actually it's not the GPA, it's the grade. The grade is a 3, plus 4 multiplied by the probability that a grade is a 4. And you're going to interpret this exactly the same way as you would interpret a mean. So this has to be a long-term interpretation. So if many students in business stats were chosen randomly, the average grade would be about 3.222 grade points. So that's it for today. Hopefully that works, and we'll see you next time here for more AP Statistics.